I'm calling this Geometric Sequences Part 2. It's on page 17 of your unit handout. There's nothing new here that we're learning in terms of ideas or concepts. So there's nothing new we're learning here in terms of math content. What we're looking at is different applications of what we've already learned. So number 1 says a rubber ball is dropped from a height of 4 meters and it bounces to 3/4 of its height every bounce. So let's write down these heights. And this is going to be tricky. There's something about this question that is really tricky. Okay? So the first height the ball has is 4. My mistake, 4. Right? It's dropped from a height of 4 meters. And it bounces back up to a height of 3/4 of the height that it fell from. So 3/4 of 4 is pretty easy. It's 3. So here's what the ball is going to do. And even though the ball might be dropped straight down and it just goes up and down, I'm going to draw it kind of spread out horizontally. So this is the ground, and it's dropped from a height of 4 meters. So that's 4 meters. And then when it bounces back, it bounces to a height of 3/4 of 4 meters, which is, say, 3 meters. We don't have to worry about getting out rulers to do this. I can kind of eyeball it. And then it bounces to a height of 3/4 of that. And then it bounces to a height of 3/4 of that. Are you getting my drift here? Because it's bouncing to a height of 3/4, we can find the next height. This is 4 meters. This is 3 meters. If I take 3 times 3/4, I get 2.25. I get 2.25 meters. And I'm not going to worry about the fourth height, because I just want to establish everybody. Well, I guess maybe we can. $1.6875. And this continues on. I mean, mathematically it continues forever, but sooner or later the ball is going to lose energy and it's going to stop bouncing. Okay? But this is what's going on. So I hope that everybody understands these numbers. I can even put in this 1.6875. Form a geometric sequence. Because each term is found by taking the previous term times 0.75. All right? The question says, what will the height be after 12 bounces? Now, I guess we could continue to do it this way, but we're a little more sophisticated in stuff like this by the time we get to grade 11 math. The issue here is this. If I use this as my sequence, T12 will not be the height after 12 bounces. And the reason that that won't happen is because T1 is not the height after 1 bounce. It's the height that it was dropped from. Okay? So this is the height after 1 bounce. This is the height after 2 bounces. This is the height after 3 bounces. So if you are going to use that sequence, the height after 12 bounces is going to be the 13th term. Can you wrap your head around that? So we have an option here. We could do this and find T13. That would be our answer. We could. Or we could use this sequence and find T12. See, and I like this better. If I want to find the height after the 12th bounce, why don't I set up my sequence so T1 is the height after 1 bounce, T2 is the height after 2 bounces, etc. This is still geometric, yes? Okay. So I'm going to actually do it both ways. We can use T1 equals 4. And by the way, that's the height after no bounces. And our formula will be T sub n equals the first term times the common ratio to the n minus 1. Right? That would be our general term. If we use T1 equals 3, and 3 is the height after the first bounce, this is our general formula. Because the first term is 3 and the common ratio is 0.75. Are you all with me on this? Okay. The issue is, since T1 equals 4, and that 4 in our first method is not the height after the first bounce, our answer will be T13. Whereas since I've lined things up logically here that T1 is the height after 1 bounce, here T12 will be the height after 12 bounces. And some of you are going to understand why we're going to get the same thing. And it's going to happen pretty much as soon as I write the following. That the calculation on the left involves multiplying the first term by an extra 0.75. Right? This is going to be 4 multiplied by 0.75 to the 12. This is going to be 3 multiplied by 0.75 to the 11. Well, why are we going to get the same number? Because 4 times 0.75 once will give you the 3. And then you have 11 more multiplications. They're going to be the same. And you can convince yourself of that. Well, I'll do it, for you or with you on the calculator here. If you do it this way on the left, which, again, sorry, I just don't recommend it. I think it's confusing that you have to go, wait a minute, n is not the bounce number, n is something else. It gets confusing. But if you do use the method on the left, you're going to have 4 times 0.75 raised to the 12, which is only 0.13 meters, which is the answer. And if you do it using the method on the left, you're going to go 3 times 0.75 raised to the 11, and you get the same number. So regardless of how you think of it, that's the answer. 0.13 meters. Any questions with the first example? 2. The amount of asphalt on shingles decreases over time. I don't know if you've ever been helping somebody out and cleaning out your eaves troughs. You get all that granular crap in there. That's the weather, and Alberta weather is hard. You get the freezing and the melting and a lot of water running off. Water erodes things. So that granular crap that's coming off is the asphalt pieces that are on the shingles. And sooner or later, we've all seen roofs around town, in any town or city, where the shingles start to curl, and it gets to a point where they're not very good anymore. And even though the asphalt can be rubbed off so much, and yet the water still rolls off the shingles, shingles will need to be replaced because that asphalt also protects your attic and your roof from temperature changes and things like that. So, just because you don't have a leak in the roof doesn't mean you don't need new shingles, all right? So it turns out that when shingles are manufactured, we say they have 100% asphalt coverage. They're brand new. It's not like you bought some used shingles from somebody. They come from the factory. They have that maximum amount, which we call 100% coverage. But it turns out that they decrease by 4% every year. Now, there's something we're going to learn in this first example that is crucial for Math 30-1. So determine the percentage of asphalt remaining after 6 years. So what I'm going to do is I'm going to put for a first term 100%. And if it decreases by 4%, then it makes sense that this will be 96%. These are percentages. Are you with me on that? Okay, now here's the thing that you have to wrap your head around. The next term will not be 92%. When we say something decreases by 4%, it decreases by 4% of what it is. Okay? So if I start off with 100% coverage and then I have 96%, I'm going to show it to you this way, and this is overkill. Some of you will realize right away that you don't need to do all this. But I'm going to go back to the 100, and I'm going to find 4% of 100. And everybody in the class should know when you find 4% of something, you take that thing times 4 over 100. Right? You take that thing and you multiply by 0.04. So, of the 100, we've lost 4. 100 minus that 4. This is where the 96 comes from. You with me? Okay. What will I have after I lose 4% of this? Well, what's 4% of 96? 0.04 times 96 is this. I lose that from 96. So the new percentage will be this. And you're going to learn something here, because this is not how you're going to do this. We're leading up to something. I want to do one more. And I have a feeling the decimals are going to be quite extensive, but I want to keep them all. So now I'm going to find out what 4% of this is, and I'm going to take it away from the 92.16. 88.4736. Now, you did the calculations hopefully as well as me, so I just want to make sure you're getting the same numbers. We're in agreement on them. Okay. Okay, so I'm going to tell you, this is geometric. There is a number that you multiply each term by to get to the next term. I want you to figure out what that number is. You can take T4 divided by T3. You can take T3 divided by T2. You could take T2 divided by T1. You get 0.96, right? The common ratio here is 0.96. That should make sense. Listen to the logic. If I tell you, it doesn't matter, I'm going to get away from shingles. I tell you that a music shop, has got all their electric guitars at 4% off. So whatever price they had yesterday, it's 4% less. They've lost 4%. What that means is if it was worth the whole thing yesterday and you lose 4%, you are only going to be paying 96% of the old price. So a loss of 4% means you're left with 96%. And what's 96%? 0.96. So what's happening mathematically here is you're going from 100%, you're losing 4%. This is 96%. Percent means over 100, so that's why R is 0.96. I have a question for you. So we're just going to forget about this for a minute. If I told you that we had something, maybe the price of an item, and it goes up by 4% every year. So we're going to increase by 4%. What is R? 1.04. Because we go 100%, excellent. We go 100%, we add 4%, that's 104%, which is 104 over 100, which is 1.04. This is a very important idea in Math 30, that when you have an increase of a percentage increase, this is the pattern that happens. So you don't need to take 4% of this and get $48 or $4.80 and add it to get 124.80. I think my math is right. 4%, 4, yeah. You could instead you could take 4% of this and add it to 120, or you could just multiply this by 1.04. Okay, let's get back to the shingles problem. So, do you agree then, just clean this up, that the first term here is 100 and the common ratio is 0.96? Correct? Are you with me? You with me? Okay, just checking. The problem is, if I want to know how much is left after 6 years, T6 is not the answer to that question. It's the same thing as the bouncing ball, because T1, which is 100, is not the asphalt remaining after 1 year. So, it's the asphalt remaining after no years. If you want to use this sequence, T7 will be your answer. But I would question why you would set it up that way. Why wouldn't you instead use this as T1? It's still the same common ratio. And then T6 will be the answer. This is why this can get confusing. It depends on which sequence you use. If you use the one in brown, then I have to find T7. Because the one in brown, T2 is after 1 year. T3 is after 2 years. It's staggered. It's off a bit. To me, it's easier to just say, well, look, why don't we use the green stuff? You catch my drift here, what I'm trying to tell you? Okay. So feel free to use the brown sequence if you like. I'm going to use the green, where T1 is the first term times the common ratio raised to the n minus 1. To find the amount remaining after 6 years, well, you just use that sequence and you put in 6. T sub 6 is 96 times 0.96 to the 5, right? Do we really need to write 6 minus 1? I don't think so. So we work out what this is. And you get 96 times 0.96 raised to the 5, which gives me about 78%. And what this means is that at the end of the 6th year, and I hope you understand the shingles are not going to follow a perfect geometric pattern. It's an average kind of thing. But after 6 years of weathering, there will only be 78% of the original asphalt remaining. And that's the answer to A. Let's take a look at the answer to, or let's take a look at B. If the shingles need to be replaced when the asphalt drops below 45, then for how many years are the shingles good for? Well, here's our sequence. And I'm using the green one so that my N in the sequence matches my year. So what we want to really solve is this equation. We want to know what is N when Tn drops below 45. Right? So what we're going to do is find out what N is to give us 45, and then reason out how many years they're good for. Okay? So I'm going to put 45 here, and I need to solve this equation. Now, if I wanted to have a personal little chuckle, I could say, you know what, I gotta quickly go to the office for something. I'll give you guys a few minutes to solve this equation. And then I'd go outside and I'd laugh to myself, because you don't know how to solve this equation. You have not been taught the math procedure for solving this equation. There's nothing you can do. You could divide both sides by 96 and then stare at it forever, and you still would never find out how to rearrange it for N. So the beautiful thing is, all we are going to do is put this in for Y1, go to our table, and see when we reach 45. There's no algebraic expectation on your shoulders for this. There isn't. It's a Math 30 idea. So y is equal to 96 multiplied by 0.96 raised to, in brackets, x minus 1 end brackets. I don't need the brackets around the 0.96, although they wouldn't hurt if I put them there. And the reason is that 0.96 is positive. If it were negative, I would put the negative there. And it wouldn't be in a case like this. So my table should still be set up from last time to be automatically starting at 1 and going up by 1. I go to my table, and the shingles are still good after 11 years. After 14, they're still good. They're still good after 17. They're still good after 18. They're still good after 19. They are no good after 20. So in the context of this question, the answer is 19. Now, if you could solve this algebraically, so the answer is 19 years. If you could solve this algebraically, and do not worry about what I just did, okay, I did some Math 30, you would get n is equal to this number. If you use this number right here, if you use that number and you go 96 times 0.96 raised to, in brackets, that number minus 1, you get exactly, well, my calculator's hiccuping there, but you get 45, okay? If you could solve this algebraically and you get 19.56, you would say, I have to round it down. I'm not going to round it to the nearest number, which would take me to 20, because then it will be less than 45. So a little bit of reasoning there. The answer is 19 years. And we use the symbol A in mathematics for years. Never too early to introduce that. It stands for annum, which I believe is Latin, and it's where we get the word annual from, where we get the concept of a year from. So it's 19 years. And again, don't worry about how I solved it. It's immaterial. And we have one last question. How many terms are there in this sequence? Really easy question. Because we can't do it algebraically, we have to do it on our calculator. Take a minute and figure out for me, please, what the common ratio is. I'm going to say 1.5, just looking at the numbers. So 3 halves. We're back to what we talked about, or I mentioned last week. Since it's 1.5, which is a nice, what I call a friendly or nice decimal, it's not 1.3826 something. Let's just use 1.5. Your general term is the first term multiplied by the common ratio raised to the n minus 1. If we determine the value of n that matches up and gives us a term of 531,441, that n is the answer to the question. Because let's just imagine that n that matches with that last term is 12. It's not going to be. I doubt it very much. Then that means that that last term is T12. It's the 12th term. But it's the last term, so there are 12 terms. Right? This is kind of like when we look at our summation formulas, T sub n is the last term. So we're using T sub n because it's the last term. So you put in 531, 441 as being equal to this. And you solve it, but you don't know how to solve it algebraically. I do. I could solve it algebraically. But you don't. So you're going to put in this expression for y1, and you're going to go table hopping. You're going to find out in the table where you get a term of 531,844, or no, 441. And wherever that is, that's how many terms there are. This is why, again, some of these geometric problems are easier. 4096 times in brackets 1.5 raised to, in brackets, x minus 1. Did I skip something there? No, I got it. And I go to my table. There it is, 13th term. By the way, just because you say start at 1 for later on, for later reference, doesn't mean you can't scroll up past 1. It's just where your viewing starts. Anyway, it's the 13th term, and that means the answer to the question is there are 13 terms.